the intersection. You've got a car traveling west with this speed, collides head-on with the minivan traveling east with this speed. The cars stick together and move off with the velocity of this after the collision. So we want to know the mass of the minivan. What type of collision do we have here? They stick together afterwards. It's inelastic, and it's a specific type of inelastic because they stick together. Perfectly inelastic or totally inelastic, and that's important. So, I want to hit my rubric points here, and let's see. I think I'm going to start by actually stating that this is a perfectly wow, that came out of my brain wrong. Inelastic collision. So the momentum is conserved, but the kinetic energy is reduced. And remember, we can either talk about the impulses or we can draw them in, right, as part of our why, but we need to realize some things about the impulses. How does the impulse on the car compare to the impulse on the minivan? Any thoughts? The impulse on the car, how does it compare to the impulse on the minivan? That's a key point that you guys really, really need to study. All right, so that's good. Write yourself a note or something. Need to study how do impulses affect each other, because it's going to be a huge point that if you don't get that, you're going to really struggle continually with these concepts. We had a whole set of notes on it. If you want to look back at those, and then there were probably about 3 or 4 pages of reading. That if you want to look at, it's good. Glad we identified that before too long went on. All right. So now I need to do my momentum diagrams. So I'm going to take that direction as west, and I'm going to call that direction positive. So I have my car that comes in, and it has momentum of the car in that direction to start with. And then I have my minivan and it has momentum in that direction to start. Then afterwards, the two are one object. And let's see, does it tell me travel with velocity east after the collision? So they're going to have a momentum in this direction, and I'm going to call that CM for car minivan, since they're a new body, they're a single thing. And let's see. I think it's clear I understand the physics. Diagram gives me clear links to my problem. All the momentums are there. Impulses aren't shown. They're on the diagram, but they are mentioned up top. I could add it to my diagram, but I think I got 100% on that. Questions before we move on? Alright, let's move on then. So, the diagram actually leads me to the beginning of my problem. I know I'm going to need momentum in here, so I might as well run out to my equation sheet and grab my momentum equation, which is right back here in Unit 1. So we'll then paste that in. Alright, so that's the only equation we actually need from our equation sheet. Our setup for the problem actually comes from our diagram here. So I know that the momentum before has to equal the momentum after because of conservation of momentum. And I said I'm going to take west as positive. So I have the momentum of the car as a vector plus the momentum of the minivan, that's a vector, equals the momentum of the car minivan object, which is also a vector. And for my equation, that's based on mass of the car, velocity of the car, mass of the minivan, velocity of the minivan, equals, combined as the mass of the car and the mass of the minivan, and then the velocity of whatever this car minivan hybrid is. Now it's time to put in my numbers. Let's see. Oops. So I've got 1,300 kilograms. Good, it's in kilograms. West with that speed 12. And the minivan is 9.4 and 1.5 afterwards. I know I'll forget. So I've got 1,300 kilograms. 12. That's positive 12 meters per second because it's going west. Plus mass of the minivan. And then it's moving at 9.4 east. So that's negative 9.4 meters per second east equals 1,300 kilograms plus mass of minivan. And their final velocity, I'm told, is 1.5 east, so negative 1.5. Wow. I think we'll hit save. Last bit didn't show up quite right, so. And now all that's left is the math. So just solve for m sub m. Alright, so number 6, we've got a hammer hitting a rock that's lying loose on the ground, and we're considering it to be elastic. So right away, I started thinking, okay, what's true of only of elastic collisions? And that's where I come up with two things being true of all elastic collisions, which is that for an elastic collision, the momentum is conserved and the kinetic energy is also conserved. The impulse on the rock will be equal but opposite to the impulse on the hammer. The impulse changes the momentum. So beforehand we have our rock, and I'm going to call that rock beforehand is 0, and then we'll have our hammer, and the momentum of our hammer beforehand will be in that direction. And then let's see, let's look at them. So the rock is 0.18 kilograms, the hammer is 0.55 kilograms. So I'm thinking, okay, an elastic collision, thinking back to the interactive demonstration, when the truck hit the car, the truck continued forward because it has more mass in the car. So I think the hammer is going to continue forward once it hits it. So I'm going to say the momentum of the hammer afterwards is still going to be in that direction, and the momentum of the rock afterwards will also be in that direction. Thinking back to what I saw in the demonstration. Questions on the why before we move to the how? Key to doing this problem is realizing that it was elastic and that your momentum and your kinetic energy are both going to be conserved for the problem. So we need, if we're dealing with momentum and kinetic energy, we need both root equations. Here's our momentum one. We need our kinetic energy one. So I grabbed valid equations from my equation sheet. And now I'm going to use those two facts that I know about elastic collisions. I'm going to use that the momentum is conserved, and then use the kinetic energy being conserved and see where I get to. So, momentum of the hammer before plus momentum of the rock before equals momentum of the hammer after plus momentum of the rock after. My prediction is everything is moving to the right, so I'm just going to take that as the positive direction. So this would be mass of the hammer. I don't need that before part. Mass of the hammer, velocity of the hammer before, and I'm saying that that's positive, plus the momentum of the rock before was 0 equals mass of the hammer, velocity of the hammer afterwards, plus mass of the rock, velocity of the rock afterwards. Now, I know the mass of the hammer. I know the velocity of the hammer beforehand. I know the velocity of the hammer. I don't know the velocity of the hammer afterwards. And I don't know the velocity of the rock afterwards. So I really can't go any further because that's a single equation. I have 2 unknowns, right? In fact, if we know this, we know that, we know that, we know that, and we know that, but we don't know the other ones. So let's see where we can get with kinetic energy. So the kinetic energy is also conserved. So the kinetic energy of the hammer before. Remember, kinetic energy is not a vector. So no vector symbols here. Hammer after, rock after. One half mass of the hammer, speed of the hammer before squared, plus kinetic energy. Well, it wasn't moving, so it's kinetic energy 0. Equals 1/2 mass of the hammer, speed of the hammer after, plus 1/2 mass of the rock, speed of the rock after. And again, I know this, I know this, I know this, I know this. So I don't have enough information in that one equation to be able to solve it. So I have 2 unknowns. But luckily, I have 2 equations with the same 2 unknowns. I have this one and this one. So I know from taking algebra that if I have 2 equations with the same 2 unknowns, I can combine them and solve it. So that's just algebra. Should come up with 2 positive answers. I personally don't love spending my time on algebra, so I throw it into like Wolfram or something like that, separate the 2 equations by a comma, and be happy. Because it would do the work for me. Let me know if you need help